Hello everyone, good day. In this lecture video, we will be discussing chapter 2, as you can see here, uh, of this subject, numerical analysis. And as you can see in the title, we have solutions of equations, root finding. So you may wonder, why do we have to study solutions of equations where in fact uh, in your high school mathematics, especially in algebra and trigonometry, you study all those things, all those equations like linear equations, quadratic equations. We have absolute value equations, um, equations involving quadratic forms, no, not involving equations in quadratic form. You have also equations involving logarithmic uh, functions, natural logarithmic functions, and you also have trigonometric equations. Those equations are already discussed in your high school mathematics, especially in algebra and trigonometry. So why do we have to study solutions of equations in, especially in root finding in numerical analysis? As you can see in the question, in this question is we will extend our topic on a complicated ones. So for example, if you have x squared plus 5 cosine x is equal to 0, so how would you solve this kind of equation? Okay, so for example, if you have here, let's say, let's have this page, let's open this page here, and let's reduce it more. Okay, so for example, if you have, sorry, so based on our illustration, as you can see, we have uh, let's try some illustration. We have x squared plus 5 cosine x. 5 cosine x is equal to 0. Am I right? Where are you? Okay, so that's the right one. So, or if you have, for example, this equation, x squared is equal to 2 to the x. So you cannot solve this kind of equations in algebra and trigonometry subject. So for example, if you try to solve this one here, we have x squared minus 2 to the x is equal to 0. So how will you try to solve x? Or perhaps you can do this one. You can log both sides, like for example ln of x squared, ln of 2 to the x. So you have 2 ln x is equal to x ln 2, and then you can divide both sides by, let's say, 2x. So from here you can cancel out this one here, and you will have ln x over x, ln 2 over 2. Okay, so by guessing you can check that if x is 2, then this equation are equal. So but there are other that uh, roots that you can plug in here, that this equation will become true. So for example, let's go to the this most graphing calculator. Let's say if you have x squared minus 2 to the x, 2 to the x. So as you can see in the graph, okay, there are three roots. Okay, this is also a uh, root of this equation. Okay, there are three roots. So but this equation can be solved using, I guess, using Lambert functions. And anyway, just research on how to solve this equation. How about x squared plus 5 cosine x? This is far more complicated than uh, the quadratic equations we solve in algebra and trigonometry. So maybe how will you solve this one? You have x squared. What is a here? So our a is 1, but we cannot solve for b. We cannot identify our b, and our c is of course 0. So a is equal to 1, b is equal to, we don't know, but our c is 0. Okay, so we cannot use quadratic formula or factoring, or so this is much more complicated than uh, our problems in algebra and trigonometry, and there are a lot more. And for this, we will try to solve this kind of problem in numerical analysis. So what we will do here is notice that this is an equation, so we will convert this equation to a function. And if stated differently, we can restate this as how can we find the root p such that f of p is equal to 0, where f of x is equal to x squared plus 5 cosine x. So actually they are equivalent. So if in this form you are going to solve for x so that this equation will become true, it's the same as finding the uh, root p such that f of p is equal to 0, where f of x is equal to this one. So in this chapter we will learn some iterative methods to solve equations, and these methods are, maybe we can discuss three methods to solve the solution of the given equation. So what is an iterative method? So an iterative method produces a sequence of numbers p sub 1, p sub 2, and so on, such that the limit of the sequence p sub n as n approaches to infinity is equal to p. And our p here is the root that we seek. And be careful that we cannot compute the exact limit. So what we will do here is to stop the iteration at some large n and use p sub big N as an approximation to p. So before we go to the uh, first iterative method, let's discuss the stopping criteria as what we discussed a while ago, this statement. Okay, this last statement. So with any iterative method, a key question is how to decide when to stop the iteration. So how will does P sub n approximate P? So what we will do here is to let epsilon be greater than 0, and this epsilon is what we call the tolerance, which we will pick ahead of time. And these three are the stopping criteria. First is you can use this kind of stopping criteria. Second is this one. This is just like the uh, our previous discussion in chapter 1. Absolute error, no, not this one, but the relative error. Okay, and you can also use this kind of stopping criteria. So if difficulties can arise, so with any of these stopping criteria, it is possible to have a sequence p sub n such that p sub n minus 1 approaches to 0, but our sequence diverges. Second is it is possible to have the absolute value of this quantity called the residual, but p sub n not close to p. So maybe you can find an example uh, for this kind of two situations when using the stopping criteria. So in our numerical results, we will experiment with various stopping criteria. However, the second criterion is usually preferred over the others, this one here. Okay, so assume we have an iterative method for the sequence that converges to the root p of some function. So how can we assess the rate of convergence? So with this, let's have this definition 24. Suppose the sequence p sub n converges to p. So you are given a sequence and then you compute the limit, and the limit of the sequence is p. So if there are constant c which is greater than 0 and alpha is greater than or equal to 1, no, not equal to 1, greater than 1, such that this inequality will hold. Absolute value, the distance between p sub n plus 1 minus p is less than or equal to some constants c times the distance between p sub n minus p raised to the power of alpha for n greater than or equal to 1. Then the sequence p sub n converges to p with order alpha. So there are, as you can see, if you look at the definition, it's really hard to use this definition uh, just to find the order alpha. But there are a lot of modification of this definition, and we will explain, or shall I say discuss other variation of this definition. But before that, let's have this special case. If alpha is equal to 1 in definition 24, this one here, equation 2.1, if alpha is equal to 1 and our c is less than 1, then we say that the convergence is linear and the rate of convergence is c. In this case, using induction, principle of mathematical induction, we can show that this is true. Okay, we can reduce equation 2.1 to equation 2.2 as long as these numbers, we set alpha to be equal to 1 and c is less than 1. Okay, further, there are some methods for which equation 2.2, this one here, holds, but equation 2.1 does not hold for any c. So after computing 2.1 and we arrive at equation 2.2, there are cases where the given will hold for 2.2 but not for 2.1, and we still call these methods to be of linear convergence. So example for these are is the bisection method. If alpha is greater than 1, then we say the convergence is superlinear. In particular, if alpha is equal to 2, then if alpha is equal to 2 here, as you can see, if alpha is equal to 2, then it is called the quadratic convergence. So if alpha is equal to 1 and c is less than 1, then we can say that the definition becomes linear convergence. So move to let's move to modifying definition 2.24. Let's have other variations on how to use this definition. Okay, let's go to the open board and let's open this one here. Okay, so this is the same as definition 24. Let's make it bigger. So it says here you are given a sequence p sub n that converges to p, which is the same as in the assumption of the set definition 24, with of course p sub n is not equal to p for all n. Then if positive constant lambda or lambda here is c, of course alpha is the same as in alpha in definition 24. So this one here, this definition 24 can be restated as finding the limit of this form here. So instead of using definition 24, you can use this definition to determine if the sequence is linear or non-linear. If you could have quadratic convergence. So this is for restating or variance of definition 24. Okay, let's have this one here. If alpha the same as in definition 24, if alpha is equal to 1 and or c or lambda is less than 1, then the sequence is linearly convergent. And if alpha is equal to 2, then the sequence is quadratically convergent, which is the same as in definition 24. Let's have this one here. No, not this one. So anyway, so that's for restating definition 24. So let's have an example. Let's go back to our PDF. Okay, so right, this one here. No, not this one. Where are you? Firefox. Where are you? Hide. Let's hide this one here. And where's my PDF? Okay, this one. Okay, let me check. Okay, let's have an example. This one. Consider the sequence defined by this form. p sub n plus 1 is equal to 0.7 p sub n, and our p sub 1 is equal to 1, which is this p sub 1 is given. And another sequence is this one, p sub n plus 1 is equal to 0.7 p sub n square, and p sub 1 is equal to 1. This is also given. Okay, so let's solve this first sequence and determine its convergence, if it is linear, quadratic, or whatever. Okay, so before I forget, I think I have to show you. Let's this one here. Let's escape this one first, and let's go to, I think, F3. Okay, and let's go to this one here. Okay, I like also this definition. Before we go to the solution of example 25. Okay, so this is the definition, another definition, and this is the same as in the PDF. Okay, x sub infinity is our limit. Okay, and this first definition here is the definition of linear convergence, and in general this one here is the same as in what do you call this one, the same as in definition 2.24, this one here, definition 24, this one. Okay, so let's go back to this one here. So this is the general way on how to get the convergence, rate of convergence of order alpha in definition 24 using the limit. That is the definition. And it says here, if alpha is equal to 1, we have linear convergence. Alpha is equal to 2, we have quadratic. And also, if alpha is equal to 1 and our lambda is 0, then the sequence converges super linearly. Okay, so this is another definition. Okay, let's go now to our open board, and let's try to have a new page. And let's try to solve example 25. So example 25. Example 25. So for the first sequence is, which is given as p sub n plus 1 is equal to 0.7 p sub n, and our p sub 1 is equal to 1. So solution. So first is, let's use definition 20. Use definition definition 25, 24, where are you? definition 24. Okay, f2 definition 24 before we move to the other definition. Okay, the other variation. So how do we solve this one? Okay, so as you can see, we have, let's try this one here. Okay, when n is equal to 1, no, when n is equal to 2. When n is equal to 2, we have p sub 2. When n is equal to 1, sorry, this is when n is equal to 1, p sub 2. So replace in here, replace our n by 1. So we have p sub 2 is equal to 0.7 p sub 1, and we know that our p sub 1 is 1, so this is 0.7. So when n is equal to 2, we have p sub 3, 0.7 p sub 2, and we know that p sub 2 is 0.7, so this is 0.7 square. Let's try n is equal to 3. We have p sub 4, 0.7 p sub 3, 0.7. Our p sub 3 is this one. Okay, and p sub 3 is 0.7 square, so we have 0.7 square, so this is 0.7 to the power of 3. Okay, so if we continue, so let's say replace n by n minus 2. So we have p sub n minus, so look at here, are given this one. Okay, replace n minus 2, n by n minus 2, so n minus 2 plus 1 is n minus 2 plus 1 is n minus 1. Okay, n minus 1, so this is 0.7 p sub n minus 2. So if we continue, replace n by n minus 1, this is p sub n, 0.7 p sub n minus 1. So replace n by n, so we have p sub n plus 1, which is equal to 0.7 p sub n, small p sub n, small p sub n. So notice that the pattern, we look at the pattern, if the subscript is 3, so the exponent here, the subscript is 3, the exponent is 3. If the subscript is 2, the exponent is 2. So from that conjecture, we can conclude that this is equal to 0.7 to the n minus 2. and here we have 0.7 n minus 1, and lastly this is 0.7 to the n. Okay, so the sequence is our sequence, as you can see here, p sub n. P sub n is equal to 0.7 to the n minus 1. And if you go back to calculus 3, this sequence converges to 0. Okay, in calculus 3. Okay, let's try to apply our definition. This one here, this one here, and it says here in the example 25 that the first sequence converges to 0 linearly, so our alpha is 1, but the second sequence converges quadratically. So this is not a consequence, since as you can see in the given, this is raised to the power of 1 and this is raised to the power of 2. There are some cases where even if it is raised to the power of 2, it is linear, and so on and so forth. Or if it is rational, then there are times that maybe it is linearly convergent. Okay, so just try to use the definition. Okay, so but anyway, if it is linear, then it will satisfy this equation 2.2. But let's try to use definition 24 to show if the uh, given in example 25 is linearly convergent. Okay, so this is the solution. So notice here that this sequence is uh, convergent and the limit is 0. Just recall your calculus calculus 3. So but if you are not convinced, let's I have here the symbol. I type the sequence, but I replace n by x, and clearly the limit is 0. But anyway, it says here that this one here, the blue one, the limit of a to the x as x approaches to infinity is 0 for a between 0 and 1. Okay, so that's it. But let's go now to applying definition 24. Let's show if the sequence is linearly convergent or not. So let's apply the definition. Let's apply definition 24, and notice that definition 24 says that p sub n plus 1 minus p is less than or equal to c times p sub n minus p raised to the power of alpha. Okay, so our p here is 0, so this is our p, this is our p. Okay, 0, the limit. Okay, so let's substitute. Let's recall that our p sub n plus 1, let's move to this one here, p sub n plus 1. P sub n plus 1 is 0.7 to the n, while p sub n is 0.7 to the n minus 1. This method here is not always applicable, but there are some cases that you can use this method to explicitly express the sequence p sub n plus 1 as a function of n. Okay, let's substitute. This is 0.7 to the n minus 0 less than or equal to c. We have 0.7 to the n minus 1 minus 0 raised to the power of alpha. Okay, so simplifying, we have 0.7, okay, absolute value of 0.7 to the n, and here we have 0.7 absolute value minus 1 raised to the power of alpha. Okay, we know that our n is a positive integer, so we can remove the absolute value sign, so this will become 0.7 to the n less than or equal to c times 0.7 to the n minus 1 raised to the power of alpha. Okay, so let's try to substitute some values. So let's try if alpha is equal to 1, we have 0.7 to the n less than or equal to c times 0.7 to the n minus 1. Okay, and for n is equal to, let's try for n is equal to 1, let's play n is equal to 1, we have 0.7 less than c. We have 0 times 0.7 to the 0. Okay, so but this is 1. Okay, so what we have here is 0.7 less than c. So let's try n is equal to 2. 0.7 square less than or equal to c. Let's try some more. We have 0 times 0.7 to the 1. Okay, let's try more. N is equal to 3. 0.7 to the 3 less than or equal to c, we have times 0.7 square. Okay, so our candidate for c is 0.7. How about if you replace by 0.8? Okay, will this inequality hold if you try bigger than 0.7? Okay, so just ask yourself if let's wait for a while. If c is 0.7, so from here our and so on and so forth. Okay, so from here we can conclude that our c is 0.7. Okay, but how about 0.8? 0.7 to the power of 3 raised to the power of 3. The answer is 0.343. 0.7, I use a calculator here, times 0.8, 343, 392. Okay, so how about based on our definition, if there exists a constancy, so we can choose c to be 0.7. Okay, so let's try where are you, PDF, this one here. Okay, not the given does not say that our c must be fixed. As long as you can find a c that this inequality will hold, then it will satisfy the definition. Okay, let's go back to our open board. How about if we try alpha to be equal to 2? How about if alpha is equal to 2? We have 0.7 to the n less than or equal to, where are you? C times 0.7 to the n minus 1 raised to the power of 2. Okay, so if we try to substitute some values of n, let's say n is equal to 1, so we have 0.7 less than c times 0.7 to the 0. Okay, to the 0 raised to the power of 2. Okay, the same as here. Okay, same as here. Let's try n is equal to 2. N is equal to 2. We have 0.7 square less than c times 0.7 to the 2. Okay, because n 2 minus 1 is 1 times 2 is 2. Okay, let's try some more, like n is equal to 3, 7 cubed c times 0.7 to the power of n is equal to 3 3 minus 3 minus 1 2 times 2 is 4. Okay, so 4. Let's try another one. I think the last one, 0.7 to the 4 c times 0.7 to the, this is 6. 4 minus 1 is 3, 3 times 2 is 6. Okay, so as you can see here, this is true for all n. Okay, this must be true for all n, and so on and so forth. So as you can see, you cannot find, no, there's no c that will satisfy all these equation if alpha is equal to 2. Okay, if alpha is equal to 2. So if alpha is equal to 1, we can, if you extend up to infinity, no, n is equal to 4, n is equal to 5, n is equal to 6, and so on and so forth, we can find a c which is 0.7 that will hold for all equations when n is equal to 1, 2, 3, and so on and so forth. No, not equations, all this inequality. Okay, so our c here is 0.7, and all this inequality will hold. Okay, so that's it for using definition 24. But if we try to what do you call this one, if we try to use the other definition, where are you, this definition, if we use this definition, sorry, if we use this definition to show example 25 that indeed it is linearly convergent, the convergent is linear, then this definition is much easier. Okay, so let's try it's somewhere here. Okay, let's try it somewhere here to show. Let's recall some. Let's recall our function p sub n is p sub n plus 1. P sub n plus 1 is equal to 0.7 to the n, and p sub n is 0.7 to the n minus 1. Our p is 0. Okay, so the question here is, how about if we cannot explicitly express p sub n in terms of n? Okay, and note that in our given, the given in example 25 is defined recursively. So what if we cannot express the given explicitly? So you can use this definition. Okay, this way of solving. So let's try limit of p sub n is 0.7 to the n minus 0 and the denominator is 0.7 to the n minus 1 minus 0 as n approaches to positive infinity. Okay, so use this definition here. Okay, we have the limit of, we can delete the absolute value sign. Our alpha here is 1. Okay, our alpha is 1. So suppose our alpha is 1. Let's say where are this one here? Alpha is 1. Okay, let's try later if our alpha is 2. So we have the limit of 0.7 to the n. We have 0.7 to the n times 0.7 to the negative 1, and approaches to positive infinity. And as you can see here, so we can cancel this out, and what we have here is 0.7 as n approaches to positive infinity. So we have negative exponent here, so we can place it in the numerator, and we know that the limit of constant is constant. So this is our alpha or our c. Oh, no, not alpha, our lambda, based on the definition here. So our alpha is our c, which is the rate of convergence, and our order is 1. So the limit exists. Okay, says here if positive constants lambda and alpha exists with this limit, then the sequence converges to p of order alpha. Okay, so how about if we try to solve it using lambda is equal to no, alpha is equal to 2. Alpha is equal to 2. So we have the limit of 0.7 to the n absolute value. We have 0.7 to the n minus 1 raised to the power of 2 as n approaches to infinity. Okay, so notice that our n are positive numbers, so we can remove the absolute value sign. So this is 0.7 to the 2 times n minus 1 as n approaches to positive infinity. Okay, so let's simplify. We have 0.7 to the n, and what we have here is 0.7. Let's simplify the denominator. 2 to the 2n, no, 0.7 to the 2n times 0.7 to the negative 2. Okay, as n approaches to positive infinity. So we can write we can move this outside, this one here. We can move that outside, so we can write this one as uh, 0.7 to the n, then 0.7 to the n times 0.7 to the n as n approaches to positive infinity. So we can consider 1 and then 0.7 square times the limit of 1 over 0.7 to the n as n approaches to positive infinity. Okay, am I right? So what is the limit of this one? Okay, so let's try our calculator here, online calculator, and let's replace this by 1 over, no, let's try this one, 1 over 0.7 to the n, I know, to the x, sorry, to the x. Okay, so the answer is infinity. Okay, the limit does not exist if alpha is equal to 2. So as you can see in our calculation, this is infinity. Okay, diverges. So if you try alpha is equal to 3 and so on and so forth, it will not work. So indeed, the given where are you? This one. The given in example 25 is linearly convergent. Okay, so you can show that the second one, letter B, converges quadratically, okay, for the second sequence, and for some values of n, as you have noticed, the quadratic convergence, this one here, is faster than linear convergence based on this table. So if you substitute for some values of n, okay, so this is for the next topic. We have bisection method. This is it for now for part 1, and this is for part 2. So I will ask the question if or in the assignment for letter B, okay, for this second sequence. So show that the second sequence is quadratically convergent. Okay, so that's it for today. Thank you so much for listening.